who would be talking to us about physics in the world around us. Professor Donald is an Emeritus Professor of Experimental Physics here at the Cavendish and the Master of Churchill College. Her primary research interests lie in experimental soft condensed matter physics and applying microscopic methods from the field to biological systems and synthetic systems like polymers and in terms of biological systems like protein aggregation and so on. And I do not want to take up any more of your time, so I would like to hand over to.
Thank you, and thank you for turning up on such a horrible evening. I will slowly drip during this talk, and I hope I will be dry by the time I'm finished. So I realized when I looked at this that physics in the world around us is actually a rather silly title, because physics is everywhere, obviously. What I meant was the physics of the things we sort of come into contact with on a daily basis. So a lot of soft matter is like that, will be very familiar to you, even if you haven't particularly tried to look for the physics in it. So the first part of my talk will be about that and some of the research I did. And the second part will be much more about the kinds of things I do now, which are more about, as a scientist working in the world of policy and funding, and some of the work I've done around gender. And I'm really glad to see there are some women in the audience, because I have given talks, certainly in colleges, where not a single woman has turned up, and it's very frustrating. Nevertheless, it's probably good that the men hear about it too. So let me start with giving you some background. The Cavendish course traditionally didn't get into discussing condensed matter at all till quite far into the course, let alone soft matter. And when I set out, which is an awful number of years ago, soft matter didn't really exist as a discipline. Condensed matter meant metals, conductivity, Fermi surfaces, semiconductors, but the soft matter end of it came in probably in the 70s, 80s, and certainly didn't get into the undergraduate curriculum until, well, I probably taught the first course back about 15 years ago. So it's making its way, and soft matter, it covers a lot of materials, and this clicker is not working. All right. All right, we'll have to do it the hard way. I don't know why this has given up. Oh, here we go. It's very familiar to you. It's lots of things that you will use on a daily basis. Bread, I did a lot of work on starch and starch products over the years. But one of the key things about the squidgy stuff is that whereas if you hit wood or metal, it doesn't deform when you do that. The soft stuff, it's soft, it deforms. And so it may deform under its own weight. It can often be shaped very easily, spread, and it's very different from metals and things, stuff like that. So the properties often change a great deal with heat and cold. So if you think about butter and margarine, in the winter and in the summer, it behaves very differently. It's very sensitive to temperature, and that is another quite common attribute. And so it's very much familiar, changes shape on time scales that are seconds-ish, unlike the vibrations of atoms and molecules, which are 10 to the 15 or something. And it's contrasted with metals and things like that, as I say. So let's look at some examples. Here are some very homely examples: shaving foam, foods, shower gel, glues, skin creams, gel packs for sports injuries. You'll have come across all of those. Also lots of biological examples. So slug slime, the trail left by slugs, mucus and snot, which you will have in your bodies, marine life adhesives, frog spawn, all those are this sort of soft, squidgy stuff. So one of the key attributes, if we're talking about definition, is viscosity. And to this audience, I can use an equation to define viscosity, which I can't always. So it's the ratio of the applied stress to the velocity gradient. If you're sharing something, squirting tomato ketchup out of the bottle or whatever, you will have a velocity gradient. It's usually slower on the sides and faster in the middle. For solid flow would say it would be a parabolic flow distribution. And you can, so it's the ratio of the applied stress sigma to this velocity gradient, and viscosity eta is what one means by viscosity. And I did a lot of work on polymers. That was the first kind of materials I worked with, and over my career, I moved more and more into the biological side. And polymers are often added to fluids, like water, to control that viscosity. So if you look at the back of a shampoo bottle or shower gel or something, you will probably find the first ingredient is aqua, because they like to be fancy. That's basically water. And then there will be other ingredients. There'll be things like perfume and stuff. But key will be quite small amounts of polymeric material, which will very much modify the viscosity of pure water to something thicker. And you think you're getting a lot for your money, but you're still basically getting water. So, well, my pointer worked. If we, no, oh yes. So a polymer chain, the simplest kind of polymer chain is something like polyethylene, polythene bags, not very useful as a viscosity modifier because it doesn't dissolve in water. But something like that, it will have hundreds of and thousands of repeats. And in polythene, each of these repeats is just CH2. So carbon being tetravalent, you can string these together to make long chains. And the key thing about polymers is they are long. If you think about something like sugar, it's a small molecule, it's carbon-based, it's a small molecule. You can put an awful lot of sugar in your tea and it won't change the viscosity. But the longer the chain is, the more you will modify the viscosity, as I'll show you in a minute. So CH2, CH2, CH2 repeated n times, that's the simplest kind of polymer you can have. But there are many different kinds of polymers, things like perspex, polymethyl methacrylate, or polycarbonate, which bicycle helmets are probably made out of, polyurethane. There are lots of different kinds of synthetic polymers. But also you should recognize that proteins are in fact polymeric. They're long chain molecules, but in that case, each of these little repeating, well, each of these units will be different. There will be a very specific sequence of amino acid residues along that chain. And that sequence is absolutely fundamental to how the protein can function. If you start to denature the protein, if you heat it up, if you add acid, you change the specific shape of the protein, it will unfold and then it will behave essentially like a polymer. So one of the key things, one of the reasons that polymers affect viscosity so greatly is that they are long, they get tangled up together. So even if you've only got a few short chains, a few chains, if they are long enough, they will tangle up. So the example I show you there is actually a nest of garter snakes they're native to the United States. And you can see that bit that I've drawn a red circle around, the snakes are tangling over each other. And you can think of that as what is happening in a dense enough collection of polymers. And the longer the chains are, the more they get tangled up. And if any of you knit or sew, you will recognize that it is very easy for your knitting wool or your sewing box to get into an awful mess without really doing anything to it. They just get tangled up, and then it's very hard to pull one chain out from the others. And that is essentially why, if you put polymer chains into water, the water thickens up, because you can no longer get flow occurring so easily, but you've got the resistance of the entanglement. And the way chains polymer chains are said to move is known as rotation, after snake movement, essentially. And a lot of the work rationalizing what happened when polymer chains tried to move was done in Cambridge. Sir Sam Edwards, who was Cavendish professor for a number of years, and I can't remember the dates, was very involved with theories about how viscosity was modified by polymer chains. So small number of long chains will make an enormous difference to the viscosity. But in fact, the first area I got into polymers was looking at solid polymers, and the entanglements still play a part. If you have something like a crash helmet and you fall off your bicycle and you smash your helmet on the ground, you will get some kind of deformation occurring. And how much deformation occurs will depend on how many entanglements there are per unit area. So polycarbonate is a very useful material for crash helmets because it's got a dense array of entanglements. Something like polystyrene has a much less dense array and is much more brittle as a result. And that was the first project I got involved in when I started work on polymers. So much of soft matter is structured by the presence of these entanglements. Now, entanglements, as exemplified by those snakes, are obviously temporary. The snakes can move, they will follow their head, that is how the chains move. Those are temporary entanglements. But in something like a rubber, you chemically link the chains together. So crosslinks will be permanent chemical junctions. Entanglements are long, light-lived, but not permanent. And you can also have lots of other ways in which the fluid is structured, as I'll show you in a minute. So I mentioned that I'd done this work on mechanical properties of solid polymers at the start of my career. Fast forward through several decades, and I moved into biological materials. And I was looking at what happens when you structure fluids with proteins. So something like yogurt, a milk-based product, will contain beta-lactoglobulin, which is one of the main milk proteins. And in its native state, it will exist in a very carefully bonded, carefully structured way. So an individual protein of beta-lactoglobulin will have some helical structures shown in red there, and some so-called beta sheet, which is sort of zigzag. That the specific sequence along the chain will give rise to a very particular shape. That shape is crucial for its biological function. But if you heat it up, or if, as in yogurt, you acidify it, that structure will break down. It's usually stabilized by hydrogen bonds. The hydrogen bonds will be broken up. If you break the structure up enough, it will just go into a completely random coil structure. But there are intermediate states where it's partially unfolded. And in that case, the beta sheet regions shown in blue can line up to give long ribbons of beta sheet. And that will structure the fluid in very acid conditions or neutral and above. So this is the pH scale. You will get a fibrillar structure that the fibrils consist of this alignment of beta sheets. And that is actually the same structure as you find in amyloid fibrils, which underpin Alzheimer's disease and other diseases. That's not to say if you eat yogurt, you're going to get Alzheimer's, just to make that clear. But we actually started off looking at what happened in the intermediate pH range, so around pH 5, where a very different kind of structure was seen. These are transmission electron micrographs. This is a scanning electron micrograph, and I apologize, it's in length scale. So these particulate structures are of the order of hundreds of nanometer in diameter. They will also structure the fluid. They will aggregate and therefore provide resistance to flow. So around pH 5, you get these particulate gels, fairly monodisperse. And we started looking at them because we wanted to we had a new kind of electron microscope, which let us look at structures when they were wet. So these are all in aqueous solvent. And if you try and look at something in aqueous solvent in a conventional electron microscope, which operates in high vacuum, you pull the water off, the structure can collapse, and you can measure the size of the particles, but you don't know really how relevant that is because they're dehydrated. And we had at this point, got a new kind of electron microscope called an environmental scanning electron microscope, which had the resolution to look at these particles that were hundreds of nanometers in size. And the key thing about this is around your sample, you keep saturated vapor pressure so that you can stabilize the water in the sample. But the distance that the electron beam travels through that saturated water vapor atmosphere is very, very short. So you don't get the scattering of the electrons that prevent high resolution images being found. And so we turned to look at these particulate gels, not initially because we were interested in particulate gels specifically, but more because we were trying to see what this new kind of electron microscope would do. And we had, I think, the second of this kind of microscope in the country when we started work. You know, this work was done long after that. And I should just say, before I go on to look at the analysis of the particles, we did also look at structures forming in the very acid conditions when amyloid fibril structures formed. And one of the phases of matter that isn't particularly discussed in the early years of the physics tripos are liquid crystals. And I've done a lot of work on liquid crystal polymers by this point. And if you have a lot of long, somewhat rigid chains, and you push them in enough concentration, they will align. And that is the liquid crystal phase, and that is what underlines this display. You can switch these if they're synthetic and responsive to an electric field. But we thought that if you have a lot of long fibrils, you would see liquid crystalline phases. So we looked at what happened in the polarizing microscope, and it wasn't at all what we expected. Instead of seeing homogeneous liquid crystalline phases where you had alignment and you had optical anisotropy, you did indeed have optical anisotropy, but you had these very characteristic structures which are reminiscent of what you would see if you looked at a polythene bag under cross polars. You get these so-called stereolytic structures forming. And this Maltese cross structure tells you something about the alignment. So these are large structures, they're tens of microns in size typically. These are actually in insulin, which form particularly perfect structures. Beta-lactic globulin showed slightly more irregular ones. But when we were trying to rationalize these, we realized that if you look in the literature, you could find similar structures in all kinds of different proteins, and no one had really talked about them. And when I started traveling around talking to biochemists, say, about what we were seeing in insulin and beta-lactic globulin, they said, is that the crud at the bottom of the test tube? We never look at that. We're only interested in fibrils. So that was quite an interesting diversion, if you like. We spent a long time trying to analyze how they formed, when they formed. But essentially, most proteins will form these kinds of structures under the right conditions. They may be, in the case of the proteins that underpin Alzheimer's, they may simply be a way of trying to get the misfolded protein out of the system. They are not, well, they're not toxic per se. They're probably the way of trying to get the toxic elements out of the way. And they certainly aren't going to help you cure Alzheimer's. I'll come back to why I mentioned that later. So there's kind of universal behavior in these low pH conditions. But if I, sometimes this works and sometimes it doesn't. If I return to the particles themselves, we were trying to look at how the particle size varied with conditions under which you denature the protein. So we were using heat, in fact, rather than acid, but in the case of studying the proteins. We heated in a differential scanning calorimetry pan, which allowed us to do it in a very controlled way. We got some results that surprised us at first. So the first set of data we got, this is looking at the temperature to which we'd heated the sample and versus the particle size. And there was this curious peak. At the highest temperatures, there was no real dependence, but there was a peak in the size at this sort of intermediate temperature. And we spent ages trying to come up with a reason for that. And then we realized that what we had done, we had very carefully controlled the thermal history. We had heated the samples for 10 minutes to each of these different temperatures. And of course, at the lower temperatures, the kinetics are slower, and we had failed to reach equilibrium. So if you hold for longer, this blue spot here is what happens if you hold the sample for longer to allow equilibrium to develop. And in fact, it's just a monotonic curve, which makes much more sense. And you can see for different temperatures, how long it takes to hold the sample at a given temperature to get a plateau, which is the equilibrium value. So we found that the particle size was smaller if you had a higher temperature. If you changed the heating rate, a faster heating rate gave you smaller particles. There was no dependence on concentration, although the strength of the material you generated depended on concentration. And in order to model what was going on, we used a simple nucleation and growth model of the kind one would use for crystallization, in fact. And so you just have to allow for the fact that you generate more of the material that can aggregate as you heat the temperature, as expected from unfolding kinetics. That model has nothing specific to beta-lactoglobulin in it. And that is interesting because the food industry, which are interested in this, had always assumed that beta-lactoglobulin was a good gelling material because it forms sulfur bridges. There's quite a lot of sulfur in the protein residues. And our model said, no, there's nothing specific. This is just what happens when you unfold any kind of protein. And we went and checked it and looked at a range of different proteins. And just as with the spherulites, you see the same kind of behavior. The details of the size of the particles that form under a given heating regime will vary, but you see these particulate gels. And so this is for 6 different proteins. And as a physicist, I like universal behavior. So I find spherulites in protein aggregates. That seems to be quite useful in the highly acidic conditions. In the less acidic conditions, we have this universal behavior and a model that will fit the protein behavior in this unfolded, denatured, non-native state. So that was very satisfying as a way of taking a really messy material, because food is basically messy, and making some physical sense of it. And I feel when I started working in this kind of area, and I started working on food, the first part of that was starch, there were a lot of people who said that's not physics. And it is. You can apply basic laws of physics to just about anything. And just because it's every day and you can buy it in a shop doesn't mean it doesn't have physics in it. And I feel very strongly about that. So going into the biological realm, as I did, and it's all in the past tense because I'm retired, going into the biological realm at the time was seen as a really bizarre thing to do. And now it's very, if you like, fashionable. There are many groups in this country, around the world, who are doing fantastic work in ways that are far removed from soft matter, but are absolutely bringing physics to biology. And it's been very heartening to see that transition. So I'm now going to switch gear and move away from experiments and talk about some of the other things I've done. And in the last part of my career, increasingly, I moved away from the bench. I moved away from supervising students and moved into a range of different areas, as I'll show you. And I feel the fact that I was an established physicist, an established scientist, I was an FRS by the time I started moving into some of these areas, fellow of the Royal Society, gave me clout, gave me a voice, a platform, which I hope I've used to good effect. So first of all, as a practicing scientist, it's very easy to think, I'm just going to sit at the bench, I'm going to write my papers, I'm just going to live in my little bubble, and I don't care about the rest of the world. And I think that's irresponsible. In just about every big societal challenge at the moment, we need scientists involved. And it is our responsibility to make sure that if we are doing work that is relevant to climate change or something, nothing I've said has been relevant to climate change, we should be speaking out about it. We cannot assume that we get taxpayers' money, as we typically do for our research, that we should not feed back what we're doing in ways that are comprehensible for them. It doesn't mean that only very applied work should be funded. Underpinning work is absolutely crucial. If you think about the development of the AstraZeneca vaccine, that relied on 10, 15, maybe 20 years of basic science in order to get to the point that when this crisis arose, they could take a platform and turn it into something useful very fast. And we should be willing to engage in all kinds of ways with the public. So science festivals, that's sort of obvious, but other kinds of culture festivals. I've talked at the Hay Book Festival without having written the book. And I've talked at a philosophy festival, trying to take ideas as a scientist to a wider audience. Outreach in schools, and some of you may already be doing that, acting as STEM ambassadors or something. I've had a blog for many years, though in fact it hasn't had that much science in it. It's more been about what it's like to be a scientist, which is slightly different. And ditto, I've written for mainstream media. And one should be willing to appear as experts in the media. I have to admit, I have always refused to go on something like Question Time because I just don't think I could cope with that kind of real political argument. But some people do, and more power to them. We should also be willing to engage with policymakers. Very few politicians or even civil servants are scientists, and they need to know what the science context is of the decisions they make. Again, I will come back to the energy transition. It was very noticeable back when Maggie Thatcher was Prime Minister, which was long before, I think, anyone in this room, apart from me, was born, but she went and talked to the UN about the greenhouse effect before it became known as climate change. She was a chemist, she was a trained Oxford chemist, and she could talk knowledgeably about it. It was true of Angela Merkel during the height of the pandemic, that again, she was a chemist who could get hold of what exponential growth meant, while an awful lot of politicians hadn't a clue. So one should be willing to engage with policymakers. However, any individual scientist will have strengths and weaknesses, and some should not be let loose in a school because they couldn't talk to someone of, who hadn't already got a degree in physics or whatever. And some will not want to go on Question Time, that's me, and some won't want to go and talk to policymakers. We have to work at earning the public's trust. The pandemic, I think, helped that they did believe scientists knew what they were talking about, and it's important to listen to them, but that's not always so. And I think sometimes scientists are very bad at thinking that if I just say it a bit more slowly, they'll get it. And sometimes they don't want to get it. And I'll come back to that in a minute, because I think it's an important lesson. Learning how to engage. I've had various lots of media training now, for which I am very grateful. Many years ago, so back in the 90s, I got awarded a large grant to work on colloids, different class of soft matter. The particulate gels are actually examples of colloids. They are two-phase systems where one of the phases exists at the kind of micron level, micron or sub. And they have a lot of surface area, and that controls their properties. The surface energy is a very important part of that. So paint, mud, detergent, beta-lactoglobulin aggregates. These are examples of colloids. Now, I tried to explain in a press release when the university wanted a press release about this large grant we got, that lumpy custard was an example, because if you've ever made custard or white sauce, you start off with particulates, which you try and disperse in a fluid, typical colloid. And if you don't get it right, you will get very lumpy custard or white sauce. So I tried to use lumpy custard as an example, and it was a bad mistake because I got this kind of headline. I got really quite hostile interviews, to the extent I just refused to do any more local radio or whatever. I got accused of only working on lumpy custard because I was a woman and, you know, domestic science, cooking, I could cope with that. So it was all very unfortunate. For about 15 years, I wouldn't talk to the media at all. But as I say, I've had media training since, getting a bit smarter about that. So if we take the example of the protein aggregate, so this is actually beta-lactoglobulin, and this lower one, the caption hasn't appeared. These are slices from the brain of a patient who died of Alzheimer's. This was a collaboration I did with someone who was much closer to the real medical situation. And so I studied protein aggregation that might be vaguely relevant to what happens in the brains of Alzheimer's patients. But I am not about to cure Alzheimer's. And I tried, when I was interviewed for a profile in The Guardian, I tried to be very careful and make sure the journalists understood what I was doing. And they, when they wrote this up, got it pretty well right. She turned her attention to the way protein molecules stick together, which could help reveal what causes Alzheimer's disease. It's not too far off the truth. A couple of years later, they wrote something else. I can't remember. I'd appeared in the list of 100 women who did something, or can't remember why, but they just took that interview and sort of hacked out a bit. And by this point, I was researching unconventional areas for a physicist, such as revolutionary treatments for Alzheimer's. Nope. And then when I talked at this philosophy festival, they just took that, the second Guardian one, and said I was revolutionary. You cannot win with the media, basically. They will do what they want to do. And all you can do is try and talk to them very carefully. But if ever you get doorstep, just be careful what you say, because I have occasionally made some gaffes. To come back to the point that as a scientist, we may think if we just say things carefully enough, people will get it. I read this book by Mike Hume, who's now in Cambridge, Why We Don't Agree About Climate Change, quite a long time ago. And it's a really good book in explaining why people have different perspectives on things. It's not just about the scientific evidence. And if you're talking to a policymaker, you really have to understand that. So there are lots of different things. What your cultural background is, your religion and your faith, you may have very different attitudes towards things. And that includes not having any religion at all. You may think that what matters to you is much more important than what happens to your grandchildren. And that attitude may change as you get older. So you may, you know, even if you're trying to do an economic argument, you may weight things differently. The whole basis of how you put economic valuations on something, it's very hard to do in many cases. You know, what is the value of a museum? How much does it do for mental health? These are serious questions, and people, civil servants, will be trying to come up with the answers. But how you do that calculation will affect what you think is the right answer. Freedom for the individual versus the good of the state. Again, that was very clear in the pandemic. You know, this country was all about freedom, and other countries represented here were not, or are not. And also our willingness to accept risk. You know, you may be prepared to get on a motorbike and go at 100 miles an hour, but not everyone will. And so how you value risk, and the risk of an extreme rainstorm, whatever, you know, that may affect what decisions you make. And policymakers will take evidence, but that is not the only thing. They are worrying about, are they going to get elected at the next election, or are they going to lose their job, or whatever it may be. There are lots of additional factors, and as scientists, we should recognize that. One of the things that's frustrating, I think, when scientists do interact with policymakers is that these other factors that the policymakers take into account are often not made clear. So you give your evidence, you think, I've absolutely made the case why this should be so, and the policymaker does something else, and you think, why? And then you find that there are, you know, you're trying to win votes in this district or whatever it may be. And I think as scientists, we're not trained to think about how to put an argument. I think very often it's certainly as a student, no one said to me anything other than here are the facts. And one does have to try and be persuasive. And I think social scientists are much better at that than we are. And I think the more we learn about that, the better in trying to influence things in ways that science thinks things should go. Now, I've done quite a wide variety of different roles, so I just zip through a few to give you an example of the breadth of where I believe, as a scientist, I can make a contribution, and to help orient you on the kinds of things that scientists can do. So the European Research Council is a major funder of research across the EU. We are, of course, in this country, no longer accessing it. We may yet get back into it, but at the moment, we cannot access it. But from 2013 to 2018, I was a member of this scientific council, which was the sort of top level grouping, and that included across Brexit. So the referendum in 2016 will probably not mean as much to your generation as to mine. It was a real horror when one woke up in the morning. Well, for me, it was a horror. I woke up in the morning and found we voted to leave. And I was in Brussels the following Monday, and the Europeans were horrified too, because whatever they think about British politicians, they knew we were a balancing act against some of the things that parts of the rest of the EU wanted to do. And they were very sad to see that we voted to leave. Now, much of the work much of the science that is funded in this country, often you have to demonstrate impact. It's harder just to do pure science. That was never the case with the ERC, which always funded only the science itself and not what was it going to lead to. It does lead to a lot of impact, but that wasn't a criterion. And it didn't matter which part of Europe you came from or anything like that. But much of our work concerned at looking how panels behave. Were they showing bias? For instance, what could we do to get more applications from countries that were less successful? Statistics around success rates to check that there was no bias in the procedure. Another role I took on, which turned out to be incredibly useful for becoming master of the Cambridge College, so it wasn't why I did it. I chaired the Royal Society's Education Committee. The Royal Society is the National Academy of Science, and education in this sense meant school education. And most research scientists aren't very close to school education. And I've been going through sort of a tough time in Cambridge for all kinds of reasons. And I thought, yeah, let's go and do something different. I know nothing about this. And they said, no, that's what we want. We want someone who doesn't know anything about it. It was a strange explanation, but I think they felt that there were people who had very strong views about what should be done, and they didn't want someone who was going to come with preconceived notions. But it was a time when the national curriculum was being completely rethought. The government was putting out endless consultations about should we do this, should we do that, and then didn't appear to listen to the answers. But I got into a lot of meetings with various of the ministers. Nick Gibb, who is back in for about the 5th time as a schools minister, and Nick Gibb has a reputation of being very traditional in the way he wants school subjects taught, and he gave me a London Division sum to do. And I said, I'm sorry, I'm not doing that. I don't think that's the right use of this interview, which amused the civil servants in the room no end. And we watched, or I watched, the interplay between the Department for Education and Business, Energy, Innovation and Skills, or whatever BASE stands for these days. And you learn that not all civil servants like each other. They have very different portfolios and they approach things differently. It was a lot of work. It was supposed to be 3 meetings a year, and I was spending about 2 days a week in London. But I learned a great deal. I learned about pragmatism. I learned about writing and lobbying. And I received my second lot of media training at this point. I'll skip over that, I'm conscious of time. So what I'm doing with the Royal Society predominantly at the moment is I chair a group looking at research culture. So that is looking at the research environment across the United Kingdom. There are differences between Scotland and England and Wales and Northern Ireland. So on Monday this week, we had a session with the Shadow Minister for Science, a woman called Chi Onwurah, who's the MP somewhere in Newcastle, and she was a practicing electrical engineer, very involved with setting up networks. I think she did some work in Africa. She's of Nigerian heritage, and it was very interesting to hear her talk and to hear what a Labour government would do around science if they were elected. The group has done a lot of work about the scientific workforce. I am very concerned about people who support the scientific research that one reads about, the Nature papers, whatever, but the technicians, the people who also make so much difference to our manufacturing, who keep equipment running and things like that. So not people like you who are getting an elite education, but people who perhaps have left school quite early and need to constantly upskill. And we don't, in this country, have good paths for that. We're very bad at that. So that's something I've been pushing on something of an open door. I got involved with the Department of Culture, Media and Sports. I chaired their Scientific Advisory Council for a couple of years. And that was exactly when I saw economists trying to work out what is the value of a museum. If we have free museums and people come in and it helps their mental health, what is the value of that? And it's such a different way of thinking about, what science can do. Another question we were trying to address by the time I stood down was, we talk about you must eat 5 portions of fruit and veg a day, but what's the evidence for that? Who picked 5 as the relevant number? Don't think there is any good evidence, actually, not for that precise number. And I, as a physicist, knew nothing specific about any of the questions we were asked, but I knew how to ask questions, if you like, and to challenge people. And it was a fascinating experience. So the Department of Culture, Media and Sports used to be, they were sort of grown out of culture, so museums, and I've been a trustee of the Science Museum. And they produced a report about how could they use science across the whole spread of their activities. And there were about 7 of us on the committee, and there was someone who was from heritage, there was someone who was a sports scientist, there were all these different people, and each of us read the report and said, but why are you not thinking about this, or why don't you interact with that research council? And I was quite worried because we were being so critical, and they said, gosh, that was really helpful, because I think they knew they were stuck in a sort of place they needed to move away from, and they didn't have scientists. Now, I will finish, I'm speeding out, I'm going to finish with talking about some gender issues. I spent 4 years being the university's gender equality champion, and there are so many places where gender issues are talked about now, but we don't find solutions. So Breaking the Silence was the campaign that the university launched 2 years ago, I think, about harassment, gender pay gap, Me Too, also about harassment. A lot of the work I was doing at that time, the role only dealt with staff and not with students. I think it's changed. And so we were trying to do a lot of things that would help the researchers, to make sure that there was a level playing field for men and women within the system. And just to show you, and I think the audience in the room, I don't know what the audience is like online, show the kind of problems. This data is quite old, but it's very interesting. So this is choice of what subjects you do if you're a scientist at school when you make your A-level choices. So B is biology, C is chemistry, P is physics, and the size of the letter there indicates the relative populations of males and females who take those different combinations. But if you look at it by gender, there's huge difference between girls and boys. You can see that B, biology, dominates for women, and P dominates for boys. So what is it about our schooling that leads to it, or our society? And it's, well, I've just written a book on the subject, so, we start off, it's not surprising there aren't many women in the room because we lose so many girls at an early age from physics. And And clearly, how schools teach is very relevant. And this year, the Commons Select Committee was taking evidence about diversity in STEM. And this woman, this head teacher, Catherine Bolsing, said, I think girls just don't know hard maths, and I haven't put it in, but she did essentially say something like, I think, I guess. She didn't know, she'd never stopped to think about this. And there was just sort of uproar amongst the community. I got rung up by someone from Guardian and said, would I like to quote about this? And I said, I was in the middle of the conference and I said something rather offhand and it got quoted. It wasn't wrong, but I would have phrased it better if I had more time. But they had another session and I was called to give evidence at this further session. And it was really encouraging because I think that the select committee, it worked out this was rubbish and they wanted to get more evidence. They haven't produced their report yet. This was in May. I think they were trying to get more evidence to counter this view that was clearly outdated, shall we say. And recently I also gave evidence to a Lords Select Committee on Skills. So I think it's interesting that's two committees in Parliament in the last 6 months, and I've never done one before. It's quite daunting, particularly when my laptop packed up when I was trying to do the Lords Select Committee, and I lost all audio. I hadn't gone into London because I'd had COVID. It was a disaster. Right, I'm going to skip over this, I think. But if one looks at what happens, why do we see such different A-level choices and career choices amongst men and women? And I think you can go right back to very early cultural messages. So this is data on advertisements for toys, Wordle of what words are used for boys' toys and for girls' toys. And to start with, we shouldn't have boys' toys and girls' toys. And you can see that boys are meant to get by on battle and power, and girls on love and magic. And I think anyone in this room will work out what actually makes more difference in the world. Are you going to get further by being powerful or being magical? So I think, we give very different messages if we're not careful now. Obviously, parents can counter that. But I think our cultural messages, if you look at the media, books. So I have a 6-year-old granddaughter. She loves books about unicorns. And I'm thinking, it's just really very helpful to have very pink books too. But it's taught her to read, so I suppose one should be glad. And Barbie, so choice of toys matters. You should give boys and girls dolls and Meccano and chemistry sets and, all this kind of stuff. And instead, the media kind of influences this thing. So when I was president of the British Science Association, I gave an hour-long lecture about education. And what got picked up by the media, what I said about Barbie, which was about 2 sentences. And I said, you shouldn't give girls Barbie and not things that help them develop spatial awareness on all this. The good thing about this was I got a huge number of local media interviews. And when you explain why it is a bad idea only to give girls dolls when you're giving boys all these different toys, the interviewers got it. They said, oh yeah, I see, I shouldn't be giving my child this. I should be giving a spread of toys. And it's actually quite good because you can, it's very approachable as an argument. So I will just finish. If you're interested in policy, I fell into policy kind of by mistake. I haven't talked about my career path particularly. Awful lot of it's not been conscious. I am going to do this next. I am going to chair this committee or anything. It hasn't been like that. And I would say very few people's careers in any discipline are going to be like that. But if you're interested in getting involved with policy, if you're concerned about the energy transition, or you think Cambridge should be doing something different about its transport policy or whatever it may be, there is this group called CUSPA, which is the Cambridge University Science and Policy Exchange, which involves students and gives them opportunities to get involved with projects. So you might want to look into that. If you're a PhD student, there are routes to go and work the Parliamentary Office of Science and Technology, or with the Royal Society. So there are routes to do that if you are funded by UKRI or the Institute of Physics, and there may be other routes in. I had 2 of my PhD students take these placements, and one stayed in policy, and the other went, said, no, that's not for me, and is a lecturer in Durham. So, it's a good way of just sort of finding out whether it's something that you want to do. I do wish we had more scientists in the civil service. And fast stream entry has just reopened for that. And we definitely need more politicians and more policymakers who have a good understanding of science. So I feel it's important that Cambridge graduates go into these areas. So I will finish at that point. There are many things you can do that don't involve just doing research. I think this university is pretty bad about implying that if you're doing academic science, that's the only thing that really matters. I think that's shocking. So it's worth thinking about what else interests you. And I haven't really mentioned the media particularly directly, but the media needs more scientists too. There are some very good science journalists out there, but people writing about anything but who have scientific understanding, I think is really important. I've really enjoyed these sort of last however many years doing this, even though it wasn't something I set out to do. It's been good fun.
Really interesting. If anybody has any questions, we have our task book, which the beautiful password book. And I'm just going through it.
Hi, so I'm a Barbie physicist, and you mentioned that there's still quite a big gender gap within science and Cambridge. And well, going to study physics, I sort of expected it, but I was shocked at quite how extreme it is, especially well, when from natural sciences to physics.
Yeah.
And even more extreme, for example, mathematics, which in my mind is a similar status. Are there any particular reasons in Cambridge, you think?
Well, it's interesting you said about maths, because maths in Cambridge is much worse than in most places.
Yeah.
Yeah. And that's because they require STEP, the 6th-term entry paper. And that seems to be a huge deterrent. Also, it's a requirement to have further maths. And many girls don't do that. Oxford, for instance, has a much better gender ratio in maths because they don't either do STEP or require further maths. And I've never worked out if they actually end up with mathematicians who are less skilled because of that, because they're obviously starting from a different position. I don't know that Cambridge is particularly bad in physics. I think it's bad nationally. I think one of the problems in this country, say compared with the States, is that you have to make choices very early on. Girls at 14 are perhaps not, it's not the best point in their growth to make that decision, particularly with the cultural messages against it. In the United States, where many people don't really choose their major till, say, second year university, and they have to do liberal arts electives and all the rest of it, I think it is easier to stay in physics. The proportions do vary around the world. I mean, Romania, for instance, has a lot of female engineers. And I think that indicates just how much it is cultural and not, it isn't that girls don't like hard maths, it's they're told they shouldn't like hard maths. Cambridge isn't bad, and I will say that Cambridge women do very well in tripos. That is absolutely, I mean, there was one year, I can't remember how many years ago now, when 3 out of the top 5 in part 3 were all women. And you think, well, actually they're only 20% in the class, so that's not bad going. Oh, that's a good shot.
Hi, thank you very much for the talk. I'm a PhD student at outside internship in the Centre of Science and Policy. So
Oh, yeah.
I'm interested in policy. I just wondering if you had any advice on the resources or you mentioned one book, any other books that are of interest in policy to learn a bit more about this relationship.
One book that is highly regarded is by Roger Pielke called I can't remember what it's called, but it's by Roger Pielke, spelled Pielke, and it's about the different kinds of ways you can give scientific advice. You know, you should know if you're being an advocate or a pragmatist or whatever. So that's another good book. Sheila Jasanoff has written some interesting things. She's at Science and Technology Studies. Again, I can't remember the name of the book, but she had a very interesting discussion of how decisions were made in this country about how long abortions could be allowed for, which I think Mary Warnock was involved with. One right on the back. Nearly.
I just want to ask, can you do research and policy at the same time?
Oh, I think so. I mean, I made a mistake by becoming the University's Gender Equality Champion at exactly the same time as I did the Royal Society Education Committee. And that's really what caught my research, because they were both quite demanding. I think if I'd only done one, it would have been fine. But doing both, you know, I woke up one day and thought, oh, I haven't applied for a research grant for a long time. And certainly earlier in your career, it depends. It depends what kind of policy work you want to do. So Cuthbert, for instance, has a link with the local council. I can't remember if it's the city or the county council, I can't remember. And students work with the council on some specific problem, and it's very much you know, just a bit of time around study. Also, I mean, again, depending what kind of area you research in, your research may be directly relevant to policy, and therefore, which has never been the case with mine. You talked about Centre for Science Policy, CSAT, and they have fellows, very often civil servants from NGOs and things, who come to Cambridge and want to meet academics. And I have never yet talked to one about soft matter physics, but I've had some really great conversations with them. But if you know, if someone is trying to work out, let's go back to what is the value of a museum, and you happen to be researching public experiences of museums, I mean, that's not a very scientific example, but you get the point. Your research might be immediately relevant. There was, I think most of the examples I'm going to give is a second. But again, the energy transition, you know, is a hydrogen economy viable? You might well be doing research that was looking into how you could make green hydrogen or aviation fuels out of hydrogen or whatever, and it might be directly relevant. And then it's absolutely in combination with your research. That's just not happened to have been how I've done it, but there are plenty of people here. There's a woman called Therese Marteau who works on kind of public health. Therese Marteau sort of health and how public respond to messages about it, and she's in and out of Whitehall and absolutely keeping going with research. So yes, you can. I'm done here.
You mentioned that it was more as a business, you knew what questions to ask and how to ask them. What exactly do you mean by that? Like, how can I be supporting the situation?
Because you have to see through what someone may try and present. So it's a question, if you read newspapers, you often get told, well, you know, the arts and humanities are so important because we know about critical thinking, as if scientists don't know about critical thinking. And critical thinking is saying, I've been told this, do I believe it? And if I don't believe it, what do I need to do about it? And that's, you know, that's exactly what physicists do all the time. So that's what I mean. It's sort of not being blinded by someone trying to tell you something, but challenging it. And so I mentioned this report that BCMS had produced about how they could work with the different research councils, and yet they didn't seem to get able to get beyond, well, I can work with AHRC because they're interested in arts and humanities, and I understand that. And so saying, well, you know, as a physicist, you should be thinking about, I mean, one of the things that came up at the Science Museum when I was trustee there was, yes, it's really rather important you have a uniform sort of way of digitizing. If you're going to do, you know, digitize images or digitize text, you need a way that everyone agrees. And I don't think the museum curators would necessarily have thought about that. And it's, you know, anyone in this room could have thought about it. There's no point in having one system here and one system there and they don't talk to each other. So that's the kind of thing I mean. And there was a question back there. Oh.
So I'm just wondering, why do you think there aren't many scientists who work in policy? Is it because they are not aware of this field, they do not understand the importance of policy making, or they think that they, you know, they lack the skill that the other politicians have?
I think part of it is sort of historical almost, that in this country, in the Victorian age, when, you know, civil servants sort of started, it was Oxbridge classics graduates, basically, or perhaps history. And I think scientists were seen as something else. And I don't think that attitude in a way has ever changed. I mean, it's like, how many of the cabinet have studied PPE at Oxford? Yes, very high proportion. How many of them have a science degree? I understand that the Secretary of State for Education, the very new one, did an apprenticeship in automotive engineering, which is quite interesting, and she's a woman. So I think it's just not something that is so familiar to scientists. And I think there's also the attitude, I mean, there was a postdoc by a fellow from Churchill who I knew, who was a chemist in this department, who, when she wanted to take a 3-month position as a policy intern, her PhD supervisor, she was doing a postdoc, her postdoc supervisor said, you know, if you do that, you're not coming back here. And I think, yeah, no, that's wrong. One should be able to try these different routes. And indeed, one of the things about the research culture group that I lead is very much to think about what the head of UKRI calls porosity, the idea that you can move between different areas. And, you know, if you go into policy, you're not going to give up your research in an irrevocable way. But I think in this country, it's history, and I don't think it's true in other countries. So, you know, there are plenty of examples of, I mean, China, historically, I think has had a lot of STEM people going into politics. And I think that the sort of Eastern European countries likewise. But somehow this country has a culture which I'm sure is Victorian in origin, and to some extent there is a class element in it, I think, too, that being a scientist working with your hands is not what gentlemen do. And I'm afraid I think that attitude at some level persists among some parts of this society, very much the white middle class English part of this society.
So did you face any hurdles due to this historical reason?
Sorry, say that again.
did you face any hurdles when you were designing the,
No, I was too old for it to be an issue for me, which was an advantage. I faced lots of hurdles when I tried to work on food, I can tell you, but not when I tried to go into policy. No, and indeed, I mean, the first thing I did in that space was chairing the Royal Society Education Committee, and I succeeded a woman, Nancy Ruffle, who's now Vice Chancellor of Manchester University. I mean, the gender work was obviously different and didn't start off as policy, although it became more relevant to that when it started off very pragmatically in this university.
Thank you so much for being here. It's really interesting. Thank you so much for tackling both sides,
Yeah.
both the research and the quality side. And thank you everyone for attending. We have our last talk next week and hope to see you there.